sure. Thank you. Appreciate it. All right. So, covalent bonding. Today, we will review the covalent bond. I say review because you would have learned about this in grade 9, and then you would have learned about it again in grade 10. But, as we've previously discussed, hands up if you hear the word covalent bond and know exactly everything that's going to be in this note and probably don't need to pay attention for the next 40 minutes. Hey, that's amazing. Hands up if you don't. Hands up if you're in my biology class. So you should be somewhat familiar with this right now. All right, that's cool. So let's talk covalent bonds. So a covalent bond happens when two atoms share electrons rather than giving and taking when forming a bond. So tomorrow, well, actually not tomorrow. Tomorrow you guys are going to do safety on computers. But the day after that, we're going to start talking about ionic bonding, which is one of the major ways that atoms become stable. But today we're going to look at covalent bonding. And to understand that, first we want to just say this, which is that why do atoms need to share electrons or give electrons or take electrons in the first place? What is every atom seeking? Just like every person, maybe. Stability. Doesn't that sound nice? Stability. Isn't that aspirational? Stable day-to-day life. Well, just like you might be seeking stability, atoms are seeking stability. What I usually will do, what I'm gonna do? Usually we'll do. Well, let's do it right now. I can't see.
Can you say it? I don't remember. No, I don't do. I don't know how to fucking draw a circle. No, because how come I have to do it like this? How does it not? No, actually, this isn't circle. There's flowers around it.
Ooh, there's a cloud.
We have this box. No, I just put it in a box.
Cloud. You know what else? You know what else is in cloud?
And you said I think she was half. Do you want me to bring
What?
it over? Exactly.
That was one.
It's not
That was
thinking.
once. It was once.
Not thinking. You're thinking. So then you're real gay. Exactly. And then there's only two. I thought. Don't say that. Don't ask me. No. I can't live. Just shut up.
You know what easy it'll be?
How easy it is. Like.
What is wrong with you?
I wish I was. Hey, no, seriously. That's my visor and it's white.
It's too late. It's too. I'm actually gonna pour a Sharpie.
Yeah, you pull out a Sharpie? I swear to God. I will Sharpie you. Remember when you were scared of a Sharpie?
I was.
How scared are you? You just go like.
Remember when you were scared of raw chicken?
All right, guys. I brought a toy. Look at this. So this is, yeah, oh, very safe. This is a centrifuge. Anyone know what a centrifuge is? Yeah, it's a spinny thing. So that's its highly scientific term. So a centrifuge is used to take samples and spin them around so that you can separate them by weight. So if you have a solution of something, in this case I just put water in there to simulate, but say you wanted to take a blood sample and break it down so all you had was the blood plasma, you could put your blood in here and in the tubes, and then we run it, And by spinning really fast, the heavy stuff will get pushed, because it's at an angle, the heavy stuff will get pushed out. Hey, physics guys, what force is that?
What?
What is the force that's going to cause, as something spins, heavy things to get pushed out relative to lighter things?
Centrifugal force.
Other one.
Centrifugal force.
Very good. So I've got this running, and I have 4 samples in here. And what I have done is I have spaced those 4 samples out evenly. And when I turn it on, this thing's going to spin real fast. That's several thousand rotations per minute. I think this one's rated at 6,500. Which, for the record, like if you get your car going at 6,500 revs, that's very bad for your engine. But that's operating spec for this guy. Oh, sure. Oh, like a typical Ford leader? Yeah. Oh, you'll be the guy who's like, his car gets like 180,000 K and it's dead, and you'll be like, oh, I don't know what a piece of crap this is. Yeah, shift. All right. Anyway.
Okay. Well, it's automatic. So.
Well, everything you need to know.
Standard mode.
Yeah. So, all right. But now watch what happens if I take 2 of these out, so that now it's unbalanced. All the weight's on one side. In fact, I'm even going to take 3 out, so we can see this is like how hydrogen would feel. It's got a weight just on one side. What happened? And by the way, if I let that run, this thing would like shake apart. So I'm stopping it. Why? Why isn't it working? You're doing a great job, Betsy. Keep it up. What? Why? What went wrong? Same machine, and feel this. How much does one of these weigh? Like virtually nothing? A couple of grams, if that?
It feels like a Q-tip.
Yeah, about the weight of a Q-tip. Why does about the weight of a Q-tip make this? And I mean it. If I locked that button down and ran it like that, the screws would come off and the thing would just fly apart. It really would. Why? Instability. So you need, in this case, we're talking about a rotational mass, and centripetal force is such that if you have an imbalanced centripetal force, every time that thing is swinging around, it's pulling the whole mechanism with it. And that becomes a resonant motion. You learn about that in physics too. And so you end up with resonance, and you end up with this thing starting to shake and pull itself apart. Well, guess what an atom is? It's a big, heavy middle thing like this. Listen, that weighs about as much as a Q-tip. The big steel thing in here weighs about 25 pounds. How does the weight of a Q-tip screw up something that weighs 25 pounds? And the answer is by spinning around it really fast and having some pull on it. That's enough to make the thing imbalanced. Well, likewise, if you have an imbalanced valence electron orbital, you have these negatively charged particles spinning around the nucleus really fast, and there's nothing to balance them. They aren't paired off, and the atom will tend to shake itself apart. Put those phones away, or I swear to God I will feed them to you. I mean it. Find something to do that isn't being on your phone. So, how do atoms solve this problem? Well, they have to get a full shell of electrons. And one way that can happen is by sharing. So let's look at water as an example. And we're going to draw Lewis structures for each of these. So what is the formula for water again? I am.
Preston.
Settle down. All right, what's the formula for water? H2O is correct. And what's that look like? Well, we have an oxygen, and we have 2 hydrogens next to it. And I'm going to cheat and use, well, no, I'm not going to cheat because we're not in grade 12 chemistry here. I'm going to write it completely wrong like that. And what does oxygen look like? Valence electrons. If I'm drawing a Lewis structure of this, what's it look like? How many electrons? Check your periodic table. Everyone should check their periodic table. Don't wait for somebody else to say it. Be self-motivated, for God's sake. There's oxygen. How many electrons does it have in its outer shell? 6. Very good. So, 1, 2, 3, 4. And since I've got hydrogens on both sides, I'm going to pair up top and bottom. Is it stable? Or is it like my centrifuge here with missing pieces? Yeah, so you're not going to find oxygen like this. You know, maybe in the early like protoplasmic universe, but it doesn't exist now. And it doesn't exist now because that's not stable. What does hydrogen look like? Just one lonely little electron. There he is. Look at that. And this one, just one lonely little electron. But these both have an advantage. You know what their advantage is? They're rich. What do I mean by that? They're rich. Well, they don't, of course, because money is a human construct and they're atoms. So I don't mean money rich. They're not money rich, but they are. Yeah, they're electron rich, or they're like electron doing pretty good. They're electron upper middle class. They're real close to being electron rich. Does that make sense? Like we look at oxygen. Yeah, it's not like as rich as neon. It's way richer than boron. Stupid boron. Way lithium. Right? Like, look, it's got a lot. It's doing pretty well. It's got a nice like couple of cars, and I don't know, it pays for like Rick, phone up here on my desk. Oh, you did, damn it. Okay, sorry about that. I forgot. I'll probably do that to you about 10 more times. And whatever, this is the last time I'm apologizing for it. Next time I'm still reserve the right to be angry. Pretty rich. It's got I'm very sorry. That was rude of me. It's got a lot of electrons. And so here's the point. Oxygen's rich. Hydrogen doesn't seem rich, but it's like rich for its neighborhood. You know what I mean? My grandfather always used to say, the trick is to own like the worst house on the nicest street, because it's the cheap one. But like hydrogen takes the opposite approach, where right, like it's got a pretty nice house on like a less nice street. All of which is to say, hydrogen too is only one electron away from a full shell. So they're both really close to having a full shell. And so they make an arrangement. Yeah, and what they say is, well, if we made an orbital together, what if we made an orbital so that these two electrons orbited both of us? Now they're paired up, so they can work in opposition to each other, they can balance each other out, and they'll orbit not one of us, but both of us. And these two can also make that same arrangement. So these electrons are shared. What is the advantage here? Well, the advantage from oxygen's perspective is it now has 8 electrons in orbit around it. And we know that for oxygen, 8 electrons in orbit around it is a full valence shell. The advantage for hydrogen is it now has 2 electrons orbiting around it, which is a full valence shell for hydrogen. So by virtue of having shared electrons, now all 3 atoms have full valence shells. And because all 3 atoms have full valence shells, this is stable. But because the electrons have to orbit both atoms, this will only work if hydrogen and oxygen do what? Sure, they're doing that already. What do they have to do though? Let's say oxygen's like, hey, I want to go over there to the store. What's hydrogen got to do? Got to go with it. But if hydrogen wants to go to the park, the oxygen, the other hydrogen got to go with it. Does that make sense? They're stuck together. That's right. But they're now bound together. So, like often happens in life, they've traded independence for stability. You may experience this at some point in your life. And there's a way we usually draw this, because this would get clumsy to draw two electrons and draw them there. How do we normally draw a bond like this? Does anyone remember? It's okay if you don't. We usually just draw it with a line, just like that. I can't do this. You don't have to know why, but it's at an angle. Take grade 12 chem, you'll learn all about the angles, but just, yeah, that's how it is. And then oxygen still has how many electrons that aren't shared? 1, 2, 3, 4, 2 pairs. 2 pairs of electrons that are not involved in any sharing relationship. Does that make sense? So oxygen has 1, 2, 3, 4 unshared electrons, and that's making 2 shared pairs. And we call this a covalent compound, or what's the other word we sometimes use for a covalent compound? This is a covalent bond, absolutely. In fact, I'll label that. That's a good point. That shared pair of electrons is known as a covalent bond. Does anyone know what we call an individual particle of a covalent compound? M word?
Molecule.
Very good. Molecule. They're not quite synonyms. Covalent compound kind of refers to the thing in general, and molecule is like one of them, that is a water molecule. But in practice, we use these terms pretty much synonymously, interchangeably. Oh, colors. Oh, not this class, last class. All right. So the nice thing about this is, if we look at the periodic table, we can see how many bonds every atom is going to make. But I want to make one note. Electrons are always shared in pairs, 1 electron from each atom, which means if you're going to get up to 8, you have to have at least how many electrons to be able to play this game, to be able to do sharing. You got to get up to 8, and you can share your way there, but anytime you share, it's half and half. So if we're going to share electrons, I'm going to bring one, you're going to bring one, now we have a shared pair. So what's the least number of electrons you can have and do this? Like, let's look at the periodic table. Could lithium make a covalent bond? Can it share its way to a full shell? How many electrons does lithium have? 1. So it could go share that. So it could say, hey, fluorine, you want to share? And fluorine's like, yeah, cool, let's share. And they share. They share an electron. And fluorine's happy now because it only needed 1 more electron, so it's cool. But now lithium has how many electrons? The one it brought and the one lithium brought. So now lithium has 2 electrons. Does it have any more to share? No. Does it have a full shell? No. So can lithium make a covalent bond? No. Does that make sense? It doesn't get it there. It doesn't get to a full shell. Could magnesium make a covalent bond to get a full shell? How many electrons does it have? 2. So it could share both those, right? So it could say, hey, oxygen, do you want to share some electrons? Oxygen's like, yeah, cool. So it shares 1 electron with oxygen. Oxygen contributes 1. Then it shares another electron with oxygen. Oxygen contributes 1. Now, oxygen's happy because it has 8 electrons. What about magnesium? How many does it have? 4. The 2 it brought to the party and the 2 that got shared with it. Is that a full shell? No. So can magnesium make covalent bonds? No. So what's the smallest you could be and still make a covalent bond? 4 and 4. Beautiful. You have to have at least 4 electrons. You have to be at least halfway there. So that's the nature of the game. You have to be at least halfway there. And on the periodic table, who's at least halfway there? Carbon, silicon, and all this stuff. And so in practice, there is a tiny little portion of the periodic table that actually does covalent bonding. Helium and these guys don't need to. Why not? They're already full. So it's really only carbon, nitrogen, oxygen, fluorine, chlorine, sulfur, potassium, or phosphorus rather, selenium, bromine, and iodine. It's really just this little corner of the table that even does this. All right? We call these the non-metals, but they're like the select few. They're the guys who are rich enough that they can accomplish this by sharing. I'm going to paste this in here. You don't have to worry about it. We'll talk about it. But really, the only things on the periodic table that want to make bonds are here. And how many bonds do they want to make? Well, they're trying to get to 8. So let's just really quickly make a little table here. And we'll just stick to the key ones. But like carbon's important. Nitrogen's important. Oxygen's important. Fluorine's important. Carbon, what's it look like? How many bonds, how many electrons in its outer shell? 4. So, how many bonds does it need to make? I'm not even going to say that. I'm just going to say 4 bonds. What about nitrogen? How many electrons in its outer shell? 1, 2, 3, 4, 5. And if you look, just look at the Lewis diagram. This needs a pair, that needs a pair, that needs a pair. How many bonds is it going to make? 3 bonds. Oxygen we've already talked about. It's got 1, 2, 3, 4, 5, 6 electrons. How many bonds does it want to make? Yeah, it only needs to make 2. And fluorine? It's got 7 electrons. How many bonds does it need to make? 1. Okay, what is like fluorine? What are the other ones that, like fluorine, only want to make 1 bond? Chlorine, what else? Hydrogen, what else? Bromine, great, what else? Good. They all only want to make 1 bond. Hydrogen only has 1 electron, but it's only trying to get to 2, so it gets to join the club. Iodine needs to get to, it actually needs to get to like a lot more than 8, but we draw it as needing to get to 8. Bromine needs to get to 8. Chlorine needs to get to 8. What is like oxygen and wants to make 2 bonds? Sulfur, good. We could say selenium. I've never once dealt with selenium in my entire friggin' life, so I'm not going to draw it here. I don't know. Couldn't tell you. What am I, a chemistry teacher? What's like nitrogen and wants to make 3 bonds? Phosphorus, good. And what's like carbon and wants to make 4 bonds? Silicon, very good. And this is really it. There's some oddballs that show up from time to time, but basically, when we're making covalent compounds, these are the only atoms that can play. That's it. So any covalent compound is going to be some combination of these. But you know what the great thing about covalent compounds is? And it's why grade 12 chemistry gets to be really fun, I think, and bio gets to be really fun, because we do a lot with this. You know what they're a lot like? Lego. They're just building blocks, the bricks. So carbon, you can attach it to anything you want. The only rule is, how many things do you have to attach it to? It's got to connect 4 times. You can make any shape you want. And anywhere you want to put a nitrogen, put a nitrogen. The only rule is, how many things is it going to have to connect to? 3. As long as it does, you're cool. Anywhere you want to, put a bromine. But the only thing you need to know about that bromine is it can only connect to 1 thing in 1 spot. Does that make sense? And other than that, you can build however you want. And if oxygen can make 2 bonds, it doesn't have to make them to 2 different things. Oxygen, if it wants to, can sidle on up next to another oxygen. And how many electrons do they both have? They both have 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And they can share that pair. And they can share that pair. That's allowed. Which means oxygen atoms aren't stable, but oxygen can exist in nature stably very easily just by finding another oxygen atom and making a bond with it. And we end up with a stable configuration. You can put a double bond between anything as long as it can make 2 bonds. What are the only things that can't make a double bond? What atoms can't make a double bond? Hydrogen can't make a double bond. What else can't make a double bond? Sorry? Yeah, which is? Beautiful. They can't make double bonds because they're only able to make 1 bond. But other than that, could sulfur and oxygen stick together by making a double bond without needing anything else? Yeah, they both make double bonds. Could oxygen and nitrogen make a double bond? Sure. The only thing is, what would nitrogen still need to do? Make 1 more. Can't make it with oxygen. It would need something else. But does that make sense? Like, you don't have to draw this, but if you had oxygen here, if you had oxygen here, 1, 2, 3, 4, 5, 6, and you had nitrogen here, 1, 2, 3, 4, 5, they could share this electron and this electron, but then nitrogen would need something else. What's something else I could pair up with nitrogen so this molecule could be done? Hydrogen works, and hydrogen has 1 electron. They could share that electron, and now we have a compound. And of course, I wouldn't actually draw it that way because that's ridiculous. I'd just draw it like this. And how many nitrogen should have 1 unpaired share? 1 unshared pair. Oxygen should have 2 unshared pairs of electrons, and hydrogen has no electrons that aren't shared. Yep, you bet. And there's our compound. Does that make sense? I just put it together. You can put them together however you want. By the way, speaking of nitrogen, how many bonds does nitrogen want to make again? Yeah, because it has 1, 2, 3, 4, 5 electrons in its outer shell. This one has 1, 2, 3, 4, 5. It can even do this. We're going to share that pair, and share that pair, and share that pair. And what do we call this? A triple bond. That's right. And nitrogen will still have 1 unshared pair, like that.
Wait, can there be like 7 bonds?
No. In fact, you can't have a quadruple bond. Even though carbon can make 4 bonds, the geometry doesn't work. The last electrons just can't reach around. It just doesn't work. So a triple bond is the biggest bond you can get under normal circumstances. But again, carbon could make a triple bond with another carbon. It would just mean that both of those carbons would then have to make 1 more bond. Does that make sense? Now, it is really noteworthy. Covalent bonding lets things exist in nature that normally can't. You see, oxygen atoms are way too unstable to exist in nature. But if 2 of them bump into each other, what can they do? They can share 2 pairs of electrons, and all of a sudden, pretty stable. Nitrogen atoms aren't naturally stable, right? They only have 5 electrons. But if 2 nitrogen atoms bump into each other, what can they do? Share a bunch of electrons. And for all the stuff that can form covalent compounds, this is what they do. For the most part, they just pair off. It just works, right? If you look here, could fluorine pair off with another fluorine? Why not? How many bonds does fluorine want to make? 1. So could it make 1 bond with another fluorine? They're both making 1 bond and they're happy? Sure. What about chlorine? Could they do that? Can't see why not. What about bromine? Could 1 bromine and another bromine come together and make a bond? Yeah, can't see why not. Iodine? Yeah. And as it happens, not only can they do this, but this is what they do. So for all of the things here, they can all pair off. What are the only two things out of this menu that can't just easily double off with each other? Fluorine works, chlorine, bromine, iodine. We didn't draw it, but hydrogen works. It kind of half lives here. Sorry? Carbon and silicon, right? Because carbon and silicon need to make 4 bonds. But the rest of these can all just double up. Now, as it happens, sulfur, selenium, arsenic, tellurium, and phosphorus, they have other plans anyway. But all of these guys here, their natural way of existing in nature is just by partnering up. It's just by doubling up. And we call these the diatomic elements. So if we have hydrogen, how many electrons does hydrogen have in its valence? How many? How many electrons does hydrogen have? Good God. 1, good. Over the what? There was a beep? Oh. Actual? Stop that. And they can share, and we get hydrogen bound to hydrogen, or H2. In practice, this is the only way you're ever going to find hydrogen in nature. You're not going to find hydrogen atoms. It doesn't work that way. But you will find hydrogen molecules, H2. We call this a diatomic element. Di meaning 2, atomic meaning atoms. What are the diatomic elements? Hydrogen, oxygen, which those two you should be familiar with. Surely you've talked about O2 before, right? It is. Who taught you that? Look at him. Yeah.
Yeah, sure.
So that should feel like old news to you then. So that means if we are ever doing a reaction, or if we're ever doing something and we say, hey, oxygen gas reacts with something, you're not going to use O, because O would be a single oxygen atom. And does that exist in nature? No. You would use O2s. Yeah. The stupid word we use to remember this is Hofbrinkel, which is so dumb, which, to be clear, isn't a word. But that's okay. If it helps, it helps. You know what I like to do? Do you know what there is inside of every high school science teacher? An elementary music teacher just dying to get out. Stand up. Stand up. Everyone up. Everyone up. Come on. Get up. Because I said so.
Okay.
Is there a stretch time?
Ooh, yeah, a little stretch. Everyone, one of these. You, up. You, up. Come on. Stand. Thank you. Come on. Give me some of this. Shh. I didn't ask. Give me some of this. Oh, God. My neck is making sounds that can't possibly be healthy. And the other way. There's a non-zero probability that my head just rolls on the ground right now. Okay, one of these.
You missed the eye.
One of those. Ah. Oh, God, I'm old and out of shape. Hey, we don't use crass hand gestures. Stand up.
What? Just shut up.
All right, so here's what I like to do. We're going to remember that anytime we have to use hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine, we're always going to write it as being diatomic, because they are diatomic. They partner up in nature. That's how we find them. And we're going to remember that, but from time to time, you will make an error and you will forget that. And when you do, all of your peers will hate you, because this is what we will do. We will all stand up together and we will all recite the diatomic elements. And after a few times of having to do this because you made an error, one of two things will be true. You'll stop making the error, or people will beat you up. All right, so let's try it together. And listen, look at me. I'm going to tell you right now, if this sucks, I'm going to make you do it like 8 times. Whereas if you're enthusiastic and it's good and loud, like a good elementary school choir, then once will be good and we'll just move on. Ball's in your court, but don't think I'm bluffing. I'll do this till lunch if I have to. All right? So, class, all together now. What are the diatomic elements?
Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine.
That was pretty good. I give you a C minus, take a C.
That's
Yes.
Wow.
Sorry?
Give him the short form. Make him stand up and yell at the short form like a minute.
Yeah? Okay, so listen. Shh. So listen. In all seriousness, this actually becomes important when we do chemistry. We have to remember that these guys are never found as a single atom. You can't get easily in nature a single nitrogen atom. Most things you can, because most things make crystals. And I know it's weird to think about, but even a metal is a crystal. So like, this is aluminum, this right here. And this is a network solid. It's a crystal of aluminum atoms, which means to react with that, it is possible to pull out a single atom. In fact, that happens all the time. You can react with one aluminum atom at a time. This is made of steel, which is iron and carbon. And both the iron and the carbon, you can pull one atom out at a time. So you can react with a single iron atom, you can react with a single carbon atom. The tip of your pencil is made of graphite, which is just a network crystal of carbon. And again, you can pull out one atom at a time. So you can react with one carbon atom at a time. But hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine don't exist as network crystals. They're gases floating around. Except for bromine, bromine's really interesting.
Did you just jump away?
Bromine's super cool. This is some bromine right here. And what I really like about it is it's a gas right now. And it's a gas right now because they've got this with a slightly removed pressure. There's less pressure inside than out. But if I cool this down by about 5 degrees, it turns into a liquid. It runs along the bottom there, which is really cool. So bromine's an interesting one because at room temperature, yes. Bromine is a liquid at room temperature. In fact, bromine is one of only 2 elements that is a liquid at room temperature. What's the other one? Nope. Mercury. Gallium is fun because gallium is a solid at room temperature, but then at about 4 degrees above room temperature, it melts. So gallium is a metal that if you hold it in your hand will just melt into a liquid. Pretty cool. Sorry? Everything's poisonous if you take enough of it. Seriously, actually, everything in the world has a lethal dose. Like mercury. Take mercury, for example. Mercury is so deadly that a few, if you use something that lets it perfuse into your skin well, a tiny amount can kill you. The famous example we use in science safety is there's a woman who was literally doing research on chemical safety, and she was working with methyl mercury, which is mercury stuck to carbon atoms with 3 other hydrogens. So it's a mercury, carbon, 3 hydrogens. And this gets through skin easily. And she was wearing nitrile gloves. She dropped some on her glove. And it was able to perfuse through the pores in the nitrile of the glove, perfuse into her skin, and she died 2 days later by having like a little spill on her glove of methyl mercury. On the other hand, they used to use mercury as a laxative. Yeah, no, you drink it, liquid metal, and then, not to get too graphic here, but you could collect it on the other end, so this was reusable. And it was relatively safe because in its default form, it actually wasn't easily absorbed by the, epithelia of the digestive system. Now, having said that, don't drink mercury as a laxative. But, everything can be lethal if it gets at you the wrong way. Okay, here's what I want you to know. You can make anything out of covalent compounds. The reason we don't talk about them too much in this course is because they are just endlessly complicated. Because you can put them together however you want. The only rule is, if I draw a carbon here, how many bonds is it going to have to make? 4. What can I put on each of those bonds? Anything I want. Can I put another carbon here? How many bonds is it going to have to make? 4.
Wait.
What can I put on those? Whatever I want. Could I put a carbon here and here?
Yep.
Yeah, try and stop me.
Isn't that just
Could I change my mind and say, you know what? I want these two to be making 2 bonds with each other. Can I do that? Sure. Can I also have these guys now make 2 bonds with each other? Nope. Why not? Because that'd be 5. Can't do it. Now, having said that, what could I put here if I want this thing just to be over with? Well, actually, could I put an oxygen there? How many bonds does oxygen want to make? 2. Could I say, well, I'm going to have it make both of its bonds with this carbon? Is that allowed? Sure. What could I put here? Something that only makes 1 so we can... Hydrogen. Something here that only makes 1, but that isn't hydrogen. Lithium can't make covalent bonds. You're right, it only has 1 electron, but it can't share. Well, it can only make 1 bond. Silicon makes 4, but okay, we'll put it there. I'm going to have them make 3 bonds with each other because I'm lazy. Is that allowed? Yeah, triple bonds allowed. But the silicon still needs to make 1 more bond. Something that makes 1 bond can't be hydrogen. Chlorine, cool. What are we putting here? How about an oxygen? What's something else that makes 2 bonds? Because then I can put both of them here. Double bond. What can make a double bond? Sulfur. Is that a real molecule?
Wow.
Yeah, sure. Whoa, settle down. Shut up. Is that a real molecule? Sure it is, because it follows the rules. I can put it together. You can build anything. Does that make sense? You can build anything. The only rule is everything has to make the right number of bonds. Now, because I had all that little inspection-y bit, oh God, this is going to be a tortured sentence. Who's stressed out? Don't be stressed out. Or do, but better not to be. So, today with my biology class,
I literally thought it was
we started looking at the structure of glucose, which, whatever, is a molecule. But if you look, it may look complicated, but the red is oxygen. How many bonds is every oxygen making? 2. 1, 2. This red, 1, 2. This red, 1, 2. This red, 1, 2. That red, 1, 2. All the oxygens are making 2 bonds. How many bonds does every carbon have to make? 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And hydrogens, how many bonds do they make? 1. You can put things together in any shape you can imagine as long as carbon makes 4 bonds, hydrogen makes 1, fluorine makes 1, oxygen makes 2, sulfur makes 2. Does that make sense? We're not going to try and push it. We'll talk about naming. Yeah, that's okay. We'll talk about naming on Thursday, and then we'll introduce our first lab on Thursday. Now, I want to introduce our first lab on Thursday so we can do it on the Monday coming. So listen, look at me, look at me, look at me. Don't talk, look at me. Shh. Tomorrow, I'm not going to be here. I'm going to be at a volleyball tournament. I'm going to post on Teams, which we haven't introduced yet, but I'll have them throw some instructions up on the screen. Most of you have had me before. Did the last truck use Teams? Yeah. And Calford uses Teams. All of you have been on Teams before, whatever. Okay, listen. I'm going to put all the safety stuff there. I'm also going to put a stack of safety contracts that have to go home and be signed unless you're older than 18. Anyone here older than 18? Cool. All the rest of y'all, you can sign it yourself. Everyone else has to take it home and get signed by your parents. Look at me. I don't want to mess around. I hate nonsense. I want all the safety stuff done tomorrow, and I want the contracts signed and returned by Thursday. Does that make sense? I'm not going to drag this out. It's not going to take 3 days. It's not going to take 5 days. Listen, safety, the DSPN module, frankly, is garbage, but it needs to be done. You're going to do it. You're going to get it done. You're going to pass the test. Passing means over 85, by the way. All right? If you get less than 85, I've got a second test for you. If you get less than 85 on that, I've got a third one for you. I've never had someone fail all three, but if you did, I'd probably kick you out of the class. All right? It's easy. You can do it. Take your time. Now listen. Shh. I want to get going with labs. I can't till every single person is safety done. Haley, let's say tomorrow you're sick. You're like, oh no, I'm sick. What do you do from home? The safety stuff. I want it done. All right? The next time you're in this building, you better have your safety stuff done. If you don't, then I'm going to make you sit in my office and do it all day. But mostly I'm going to be unhappy. It's fine. I'll come to you. Whoa. I'm sorry. Did I miss a bell? I must have missed a bell. There must have been a bell and I didn't hear it, but I'm going to sit down right now. Sit. I don't do the thing. I get, apparently, that other teachers don't freak out when you people do this. I don't know why. They should. They'd be more well-adjusted people if they got some rage going in their life. But listen, now you may go. Have a great day. Damn it! Well, whatever, I said it. Get out of here.
He said go.
Get out of here. Get out of here. Yeah, if it's not, it's right on my desk. It's the weirdo. Yeah. Keep looking. Yeah, you got her. It's a weird one. How we doing? Give me a few minutes, okay? I do have some stuff for you. All right. Gonna put my bromine back. Gonna put sugar back. I'm not going to look at Teams code. I think I probably just haven't added you yet because you joined late, right? So let's do that right now. Teams. All teams.
Yeah, I thought it would automatically.
Yeah, no, I'll add you right now. Yeah, you're not on there. Remind me last name. Last name?
Oh, Bartlett.
And is it B-A-R-T? L-E-T-T.
They're expensive at retail.
Also, when taking these in, just give this to you, or is there a special spot?
What is it? Nope, keep that.
Oh, are they notes?
Yeah, the notes. Why am I having a moment? There you are. You're SE, right?
Yep.
Great. There we go. Great. It'll probably take a minute or so, but you'll be in there.
Thank you.
No problem.
And it's a shop.
It's like exactly.
Listen, a receipt came out of a self checkout machine. You were like, ooh, you straight up don't even exactly. You get
Alright, what can I do for you?
I'm very sorry.
I need what the article from bio yesterday because I didn't get to the
Yeah, no worries. Go. There's a big stack of papers in my office.
Are you sure it's the one from yesterday?
How am I? I'm not sure of anything. What am I? Am I sure? Go look, see it. If it's there, great. If it's not, come tell me and I'll print it. Yeah.
When is the volunteering tomorrow?
All day.
All day?
Yeah,
When does it
send it.
start? Good answer.
It's like school day. It doesn't have to be earlier or anything.
Oh, okay. So as soon as I come in, I just.
Yeah, just coming down to the gym.
Alright, thank you.
Well, thank you again, by the way. I appreciate it.
Oh, by the way, I found one of these. Where do I put this?
What is it?
It's
You put on my lecture and I'll take care of it. Nope. Right there. This thing. The.
Do you not know what a lecture is? No.
It's okay. Settle down, Matthew. God. How you doing? You can just, is that another one?
Just gone.
Oh, okay.
I'm trying to find the track.
There's one with a fresh bag in it in my the room back there with walls and sink and what is that damn thing called? Supply room.
Oh,
Supply room. The chemical supply room. Okay. All right.